My name is Rafał Wojtczuk. I'm from Poland, and I will speak about academic tools and real-life bug finding in win32. Some info about me. Well, as you can see from the slides, the bottom line is now better. The bottom line is I'm interested in very practical aspects of computer security. So you may assume that I won't bore you to death with some theoretical musings. But recently, because of my studies, yes? Okay. I came across a few academic tools and papers related to program verification and practical bug finding. And I think they are pretty interesting for security practitioners, so I figured out I will say a few words about them. And the lecture plans go somewhere like this. First, I will take a few words about theorem provers, which are quite fascinating tools and what practical we can do about them. Then I will discuss two powerful academic tools, UQBT and CBMC. And finally, I will concentrate on the code I work on, along with some preliminary results. We will see an example of automatic finding of unexploitable integer overflows in NWWKS DLL. And this issue was addressed by a recent Microsoft bulletin, so as you can see, this is pretty recent stuff and not something totally theoretical. Okay, we start with some theoretical background, which is interesting in itself, and well, it's also important because it will clarify some design decisions which I had to make when working with my tool. So the fact is that computer programs' behavior can be described by some mathematical constructions, and this is a common way to, well, verify computer programs or attempts to find bugs in them, build some mathematical construction, and then work on it. So the obvious thing is that we need some engine which is capable of working on such models. And this is precisely what theorem provers were written for. They are the computer programs capable of proving certain range of mathematical theories. And the basic question is, of course, what kind of theories, what input language they can accept and work on them. So let's have a look at an example. This example will be about a PVS theorem prover, pretty well-established theorem prover. And the first example will be pretty straightforward. Yep. Okay, I hope it's well visible, even for the guys in the back rows. Anyway. In this example, you can see we have three variables, ABC. All of them are of Boolean type. And we have a simple statement, lemma, you may say, that this statement is always true, right? And, well, I'm not sure if it's totally trivial or not. Anyway, we can prove it automatically by invoking the prover. It will take some time. Yes. No. Okay. And it asks us what proving tactics or prover tactics to apply. And it takes some experience to well, figure out what tactics is most suitable in this case. We can try the default one, grind. And it does its job, doing some default stuff. And the result is QED. So the proof succeeded. Okay, so I hope that was pretty straightforward. Now let's try something more complicated. Let's make some more space. Okay, this time we have n variable, which is of net type, right? So it's an integer. But also we have two variables, f and g, which are of function type. They take an integer as an argument, and they return an integer. And there goes the definition of such a term, sum fn. And maybe not entirely clear what this recursive definition means, so let's have a look at something more explicit. Okay, in fact, this definition, sum fn, is sum f1, f2, plus fn, right? And you can see, okay, this really works this way, right? This is a recursive definition. If n is equal to 0, then terminate the recursion, return 0, else return fn plus some f and n minus 1. Okay, so that should be clear. And now we have another lemma, that sum of consecutive squares of consecutive numbers is equal to this expression, right? So again, if we put it simply, if we multiply 6 by this sum, 1 square, 2 square, plus n square, it's exactly this expression. And again, I hope it's not entirely trivial. Such things are usually dealt in, high school or lower years of university. But anyway, again, we can try to prove it almost automatically. Prove invocation, prove. Try again. No, I will figure it out from the beginning. Okay, and if you remember anything from high school, you should be aware that such equations are proved using induction. So let's do exactly that. And again, it does the job, verifies it for 0, for other values it must use induction. Again, there should be some nice QED somewhere in the above. QED. Okay, so this is a more complicated example. And another lemma is that you can basically switch the order of addition. So we have a function which is a sum of f and g, and you apply sum to it. You can split it into two operations. Again, I have written it down here, right? So if you have sum f plus g and n, you can first apply this operation, sum fn, and then add it sum gn. And again, this is pretty, well, maybe trivial, maybe not, whatever. But the important thing here is that apparently, in this example, the f and g variables are unbound. They are completely free, right? In the previous example, in the sum of squares, this variable was assigned to the square function. And in this example, these variables are really free. So apparently, this tool is capable of reasoning on not only on simple variables, but also on higher order variables like functions. And let's try that. And this again by induction. Only the name of the variable changed, but it is truly cosmetics. Blah, blah, blah. Okay. Okay, so this is an example okay, maybe one thing more. If you look at this language that this prover accepts, you can see that, okay, it has variables, it has functions, right? It has conditional instructions and all other stuff. So you may start to imagine that similar tools can be made to accept even a normal program, say, written in some C code. And it should be capable of doing something with that. Okay. There are a lot of different theorem provers. The examples are PVS, Cox, CVS Lite, Simplifier. There are really quite a plethora of them. Well, the first distinction is what level of automation then offer, right? Because in this example, we saw that this tool required us to, well, specify the exact tactics we should be involved in proving these lemmas. So if we imagine that we are dealing with some larger scale programs, which may involve a lot of code, that won't be a good thing if we have to, well, give hints to the prover all the time. So this was an example of interactive prover, and also some of them were designed with high level of automation in mind. And as regards the commercial use, it happens that they are mostly used in integrated circuit design and verification. It simply happens that this integrated circuit has some specifics. It's, well, mostly described during some state transitions. And it happens that in this case, theorem provers can be really employed with some success. Okay, so to sum up, well, if you employ theorem prover to prove some program properties, the way to go is to build some large logic expression and then work on that. The other approach may be more straightforward, is model checking, sometimes described as algorithmical verification of a formal system. And again, we build some model, some mathematical model, constructed so that it mirrors the imported properties of the system, but this time the stress is on explicit transitions between program state. So we have a notion of a program state. For instance, it may include the contents of a memory. Then we explicitly state that each program instruction modifies the program state, right? It can modify the memory contents, for instance. And then the model checking, well, sort of runs the program, right? It simulates the execution, and then it tries to, well, visit as many possible states of a program as possible, so to explore the whole state space. Well, again, it sounds like a very straightforward approach, but the problem is that usually, even in simple programs, the state space is too large. It's exponential, in fact. So we run into the problem named state explosion, and basically, it's impossible to visit all of the states. So you do not have full coverage of the program execution. And of course, people have employed very, very crafty ways to, well, get around this problem, but this limitation still is valid. And continuing with theoretics, quite interesting limits which hold when we talk about proving of properties of program. At this point, I should, well, remind you or define what a Turing machine is, but for our purposes, we may simply assume that Turing machine is some abstraction of the computer. So when we say Turing machine, we think computer. And the well-known halting problem is defined. We have a program X and its input, and then we try to create an algorithm. It should be an algorithm, but if there exists an algorithm which can find out whether this given program X loops infinitely. And usually we assume that X runs on a Turing machine, right? And then it turns out that this problem is indecidable, which means simply insolvable. And this is pretty, well, unexpected issue. So that means that our ability to reason about what another program do is very limited, right? I'll say it again, it's impossible to build an algorithm which will take another program as an input, and it will tell us whether it halts or not. So even if you cannot prove that, it should be pretty obvious that, well, proving other properties is also very, very limited. And there are similar theorems lemmas about theorem provers. For instance, there is a lemma that says that first-order theorem prover may loop in a proof calculations for an invalid statement. So again, if we have some theorem prover which employs some algorithm, then if we feed it some statement which is invalid, it may loop infinitely. And okay, this issue is known to many people, but it's important to, well, think of it properly. Again, the issue is that it's impossible to build an algorithm to reason about every program, about any program, right? But that does not prevent us from trying to prove some particular programs, right? Even for undecidable problems, we can employ some heuristics which should work most of the time. And when I say most of the time, it means 99.999999%. The reason being that most of the programs you encounter in real life, say some operating system components, are really simple, right? They do not employ very complicated constructions. So if you build some reasonably, well, reliable heuristics, it should work well most of the time. And it's important to remember because, well, this halting problem is sometimes quoted on some security lists. And I saw some conversation saying something like that, okay, it's a nice program you're trying to write, but it's impossible, you know. If you can write this program, you can solve the halting problem, so give up, that doesn't make sense to work on it. And the response to such a statement is simply, okay, I don't care if my program works on 99.99% of the input, I'm happy, right? So it's important to really know what the halting problem is about. Yeah, you may wonder, what is the reason that it's impossible to write an algorithm to reason about other program? And it turns out the problem is loops, because loops are the cause of indecidability. Particularly, sequential programs are easy to prove, right? Because if the program is fully sequential, well, it can involve, say some conditional statements, but it does not loop, then it will finish in some finite time, right? There's a limited amount of instruction it can execute. So we can simply enumerate all possible execution paths. It's possible because there is a limited number of them, and then one by one check that in each state some property holds. But we have loops, right? Then when we do not know how many instructions will be executed. So we cannot be sure that we will visit all the possible program states. Okay, so you may ask, what is the way to deal with loops, how to prove properties about them? And the common way to go is to, well, construct a statement named a loop invariant, which is true in each iteration of the loop. And then if you have something like that, you can prove that after a loop exits, some conditions hold. And I intended to show you an example of simple loop proving with a tool named Caduceus. This time it would deal with a simple C program, but as you are a little bit late, perhaps you have time at the end. If there is not much question, I will return to this slide. Okay, another issue is two terms, verification and checking, which should not be confused. Usually by verification, we mean proving all properties of a program as a whole. So it usually requires to have a program specification. You must know what you expect from a program, and then you can prove that this program really does what it was supposed to do. And it's really expensive for many reasons, regardless what tools you use. But there are quite spectacular examples of successful application of such a verification approach, proving the whole of a program. For instance, often quoted example is specification of Java card API in JML, which stands for Java Modeling Language. And then it was possible to prove Java card applets, to prove properties of Java card's applets, which was pretty large achievement. But there is another idea which is pretty much explored recently. Okay, we know that proving program properties is very difficult, expensive, and close to impossible. So maybe the idea is to shift the burden to the code author, right? Say we have some Java virtual machine and we accept some applets from potentially untrusted source, and we may demand that the only condition that we run this applet is if they come with the proof of the property, of the correctness, right? If only you have a proof from an author that the code does not do, say, any harm to our machine, then we may allow to run it. And this idea with proof-carrying code is, well, a part of a larger framework, which is pretty much explored at the moment, but well, I may assume if anything will result from this research, it will be many years ahead. So we should not devote too much energy to that at the moment. Okay, and another approach is checking. Well, checking is quite a common word, but in this context, it stands in a very precise meaning. Checking means proving particular, usually local properties of a program. So we're not very interested in the whole behavior of a program as a whole, but we just want to figure out some very local properties of a program. And it's very similar to a typical security audit. For instance, if you audit a C code, right, usually the first thing you do is to check whether it uses some unsafe library functions, like strcpy, sprint, or something like that. So you look at it very locally, right? You look only at the piece of code which is around some potentially vulnerable place, and you look if it's safe. And checking employs similar approach. So you have some set of properties which are pretty local. You do not need to understand the whole program flow to prove it, and then you try to prove this. An example, pretty well-known work by a team from Stanford University, which was led by Dawson Engler before he created his own company. Anyway, they created a set of tools which were capable of, well, working on the whole source of Linux 25x. And one of the study was verification if kernel uses the user-provided pointers correctly. And this is one of the bugs which the tool found almost automatically. We have a system call named sysquotactl, and it takes an argument special, which of course is controlled by a user. And then somewhere in the code, it passes this argument to function lookup bdev. And what this function does, it dereferences this pointer directly here, right? If it's not 0, it dereferences it directly. And of course, if user passes something invalid here, say some pointer into equal to 1 or anything invalid but not null, right? Then we will get a kernel exception when dereferencing this pointer, which is obviously a bad thing. So to reiterate, the tool was capable of finding such bugs almost automatically. So it's quite an achievement. So this is an example of checking approach, right? You just focus on proper access to pointer provided by a user, and they check each invocation, well, each possible place when some incorrect operation can take place. Okay, so from now on we'll focus on this checking approach, checking only particular properties. And the question is what properties to check. And as you can see from the title of the slide, it's a good idea to focus on integer overflows. There are quite a few reasons. First of all, they are quite proliferated today, right? For instance, in the recent patch for GDI 32 DLL, over 50 integer overflow checks were added to a single library. So it's pretty impressive for me. So there was potentially 50 integer overflows in this library. So it's something very unique. They can lead to buffer overflow. Okay, let's have a look at an example in such case, if you're not totally familiar with the subject. Okay, I hope it's visible. Okay, this is an example of the function which has an integer overflow. You can see it takes some argument which is length, some pointer to data, and it tries to allocate a block of memory which will be a multiple of 16, right? Nicely aligned. So it checks whether the size is divisible by 16. If not, it adds 15, then it nullifies the lowest 4 bits. And we should here have a size which is greater than the initial length, but divisible by 16. So there is this assertion, right? That size is greater than the initial length. But of course, it's not true. This is not a correct code, because if len and then size is close to the maximal value of an integer, right, to 4 gigs, if we add 15 to that, it will overlap, right? It will become a small number. And then if we allocate only a small amount of memory and copy the initial length into this small buffer, we'll get a buffer overflow, and probably we can take control over the execution of the program. So this is an example. Okay, the important thing is that integer overflows are well suited to be searched for automatically. The reason being that usually they exist not because of some computation which exists in a loop, right? On the contrary, often a typical buffer overflow happens because you process one element of some array in loop, right? And you write some byte of output also in a loop. But in this case, again, at least when we think about integer overflow in buffer size calculation, usually there is no loop involved. And as I said before, loops are a major problem when proving properties of a program, so that's a good thing that we should not care too much of them. And it's time to introduce our first friend, C-bounded model checker. It's a tool which is capable of, proving some properties of C code. And let's have a look how it behaves in this case. It's a script that invokes CBMC. You simply pass it the name of the file, which function to prove. And if you pass it this vulnerable code to the prover, it immediately reports that the verification failed, and it even presents you an counterexample, right? So if size is initially, say, it is match, which is the binary representation is here. So if you add anything more, add 15 to that, it will overlap. It will become some small number, and then this assertion will be violated. So that's good. This tool is capable of fully automatically find an integer overflow bug. But it's even better, namely, if you fix this code. How can you fix it? It's simple. Just add some check. If size is greater than, 10,000, right? You do not expect anything larger to come by. So we exit, right? So this time there is no integer overflow, because if we get to this instruction, we have the certainty that size is small. Okay? And now run it again. And this time the verification succeeds. So that's good, because it's apparent that there is a chance that we don't get too much false positives when running these tools. If there are appropriate checks for integer overflow, it should be catched by this prover, and we will not get false alerts, which is a good thing. Of course, I could talk a little while about features about this tool. Well, the important thing is, well, it has some features which are not present in other tools. For instance, bitwise operations. Most of the tools, even which are designed to work on C code, do not feature bitwise operations. Another nice thing, it supports pointer arithmetics, function pointers. Well, it automatically, uses arithmetics with bounded integers, right? So it takes into consideration the fact that during some arithmetical operations, integer can wrap. But again, it's not very good at handling loops. All it can do about a loop is to unwind it a couple of times, right? So see what happens when you run it once, twice, perhaps 3 times, but that's all. It has some limitations, though. First of all, no source code, so the ability to customize it to your needs is somehow limited. Again, it's not possible to specify loop invariants, so invoke some advanced reasoning about loops. But as I said, we don't want to. We simply do not want to prove every loop one by one, because it takes too much time, too much resources. So that's not a big limitation. The biggest problem that I have come across is that it insists that all pointers must point to something allocated, which is a pain. For instance, if you try to prove properties of a library function, which takes which takes some pointer as an argument, right? So at the entry to this library function, you do not know whether this pointer points to anything allocated, whether it's valid or not, and simply CBMC refuses to work on that. So this is a problem. You have to work around that. It's inconvenient. And it has some other quirks like inefficient array implementations, and sometimes it requires really unjustifiably large amounts of memory. Like you prove a C code which is like 10 kilobytes, and it suddenly allocates 700 megabytes of memory to prove it. So it's pretty expensive. Okay, so we know that we want to deal with integer overflows. Now, at least initially, we may restrict to some particular operating system. And of course, initially, the choice is Microsoft Windows. I'm not going to insult your intelligence and to explain why it makes sense to find bugs in Microsoft Windows. Anyway, there is quite well-known paper by Dave Eitel titled "Windows has the lowest TCO," something like that, which is TC0, not TCO, of course. So in quite humorous way, he explains why it makes sense for a security researcher to deal with Windows, not with other operating systems. So if you haven't read this paper, it's high time. An issue which is perhaps not well highlighted is that, of course, Microsoft's binaries come without source, right? But the debugging symbols are available from MSDN for free. And it really, really helps when doing some reverse engineering, or especially when you try to reproduce a vulnerability. Because even if you find something suspicious in a code, and then you try to reproduce that, and if this function is buried very deeply in the function stack, so it may be really difficult to find out what conditions are necessary to trigger this vulnerable function. And if this function is some virtual C++ method, then you may really have hard time even to find out how it can be called. So it's really difficult. But on the other hand, if you know that this function is named something like process NNTP list response from server, or something like that, so then you can safely assume that, well, this part of code is responsible for handling responses from NNTP server, and suddenly becomes very apparent how to trigger this code. And it happens really that these functions in the Microsoft libraries or binaries have really meaningful names, and it's really helpful. So that's another thing. For instance, if you compare to, HPX or Cisco, debugging symbols are really helpful here. Okay, so we know that we want to deal with Microsoft binaries, so it turns out that we have to deal with assembly, right? So we have to somehow capture the meaning, the semantics of assembly instruction. Of course, decoding of a single instruction is not a problem, right? Each decompiler, each disassembler does it in many ways. There are a lot of disassemblers available. But the trick here is that we need a convenient representation of each assembler instruction in order to, well, employ some analysis later on. As all operating system components are written in C, C++, where we are speaking about Windows 2000 and Windows 2003 at most, not Vista or higher. So we know this is a C or C++ code, so it is important to recover some higher level construction, right? Like, I know, local variables, function boundaries, things like that, everything that comes with C. So not only we need to deassemble the library, the code, but also we need decompilation, right? And by this term, I mean really recovering almost all the properties of the source, which is important if you want to conduct some deep analysis. And the problem is there is no good decompiler available publicly, at least not a decompiler which was written precisely for this purpose. And I can hear some of you murmuring that, man, why don't you use IDA? It's perfect, everybody uses that, right? What's the problem? And that may sound as blasphemy, but IDS has numerous disadvantages, at least for my purposes. First problem is lack of documentation, besides the include files which are available in SDK. I really spent a lot of time trying to figure out the exact capabilities, well, some more advanced capabilities that IDA can offer, and it was really difficult. Simply lack of documentation is really aggravating. Of course, it's not open source, so again, you cannot fix it on the fly or adjust it on the fly. And from what I have learned by pounding and these include files, it seems the internal representation of assembly employed by IDA is very close to the assembly. No abstraction is performed. You can simply have all arguments to a single assembly instruction, but very little processing is done on that. And it happens there is a better tool available. It's UQBT, which stands for University of Queensland Binary Translator. The funny thing is, it was not created with an idea of some binary analysis or security implications of any way. The goal was a translation of binary written for one platform into another binary for an entirely different platform. So say you have a Spark binary running on Solaris, and you want to convert it into a Pentium binary running on Intel on Linux. And of course, maintaining the same semantics of the program. And it happens, this tool is capable of quite a few tricks which resemble this. In the distribution, there are numerous examples which show the original Spark program and then translated Pentium program, and that they prove that they do the same thing. And as you may imagine, if you want to translate binary from one architecture into another, you have to decompile that. You have to really know what this binary does, what is the semantic of the program. And that's why this tool is pretty useful for my purposes. This project is quite large. A lot of people worked for a long time on that. It supports architectures like i386, Spark, HPPA, MC68K, a few binary file formats, ELF, DOS, exe, PE to some extent, but they mostly focus on ELF format. But the most important thing is they have very convenient instruction representation. In fact, they have some sort of meta code, some intermediate level assembly or whatever you name it. Anyhow, it's called semantic strings. The main C++ class that implements it is called semantic strings. And this class is responsible for holding the meaning of all instructions, all assignments, all statements. For instance, the same representation is used no matter what was the architecture of the source binary. So no matter if you analyze Spark binary or Intel binary, it gets translated to the same representation, right? So it's apparent that you can abstract of any dependencies on the original architecture, which is very good. Also, they have a lot of code which work on this representation. So for instance, if you want to translate it, perform some additional analysis, it's very helpful. For instance, there is a function which takes a semantic string as an argument and some substring, and it can change, for instance, each occurrence of, say, EBP register plus something into a local variable. There's a single function to do that. And if I wanted to write it in some IDE scripts or plugins, it would really take a lot of time. And in this case, there's a lot of code were available. Also, uqbt is capable of emitting C code from assembly, so it really performs like a real decompiler, produces equivalent C code, well, more or less equivalent. In fact, all our analysis related to integer overflow finding will be done at the semantic strings level, but as we saw, CBMC prover works on the C code, right? So it's important to feed it something it can work off. So the capability of emitting C code is important. And finally, the code is with BSD license, excellent documentation. There is, as far as I remember, like 200, 300 pages of PDF documentation in the distribution, really describing every bit of functionality. So it's really great. Again, unfortunately, there are some problems when applying uqbt to at least to win32 files. There was a number of problems. Some were difficult, some were not. For instance, only CDEC calling convention was recognized because that's what is used mostly in Unix world. But unfortunately, on win32, at least 3 different conventions are commonly used. So it was a problem. Okay, there's quite a lot of things that were missing. And if you're interested in gory details, what was missing and how I approached this, you can read the paper, which is available on the Congress website along with the slides. But it's not totally important at this moment. There are some technical issues. Well, the important thing is that I fixed or worked around the above problems, right? Which took me quite a lot of time, but well, the state of the tool is now that it's more or less working. So maybe let's just summarize what we will intend to do. We will take some Windows binary. We will feed it into uqbt ng tool, which should decompile that, produce some C code, and also it will add assertions which check for integer overflows. And then if we have such a C code, we will feed it into CBMC theorem prover or model checker, which will find whether this assertion holds in each possible execution. And then we should get some either verification succeeded that it's not possible to cause an integer overflow here, or verification failed, which may mean there is an integer overflow. So the last thing is to add checks for integer overflow in buffer size allocation, right? Of course, integer overflow can happen in many places, but well, it's most dangerous when it happens in buffer size allocation. And again, it's another thing I have assumed, right? So we have this example, like we have local alloc call, which allocates memory with its library function, and takes EEX as an argument, the size. And somewhere before, we have an assignment to EEX. So the algorithm is find all calls to function which allocate memory. For each call, find an instruction which calculates the actual size, and then look if integer overflow can happen here. And as we look here, of course, we have 2 additions, right? And each of these additions can result in integer overflow. So we should add an assertion here, checking for both additions. Also, we have a multiplication. Integer overflow can happen here as well. So another assertion is due. But also, we have to find the assignments which assign EDI and ECX register, right? Because integer overflow could happen even earlier. So again, we have to backtrace the execution to the instruction which assigns EDI or ECX, and then apply the similar checks there. And to sum up, the checks are added for integer overflow in addition, multiplication, and 32-bit to 60-bit conversion, which can happen if you mix integer and short variables. And another thing is to remove all the loops, another simplification. but it's required for CBMC to function properly. And again, as I tried to convince you, it should not introduce too much false positives, neither negatives. Okay, and this is some sample results, again with the library I mentioned. But I think first we will try to run it. Okay, this is a result of a previous run, so let's remove it. Okay, this is an invocation of the tool. Yeah, some flags, it takes the binary as an argument, and mercifully I will suppress the errors. Okay, so we can run it. It will take, do I know, 30 seconds, something like that. This binary is like 60 kilobytes long, if I remember correctly, right? 60 kilobytes. And it will create like 200 functions. 200 functions. So it may take some time. Okay. So this directory was recreated, right? And as you can see, it contains a lot of files, which are, each file contains one function from the assembly. Okay, so we have the decompiled source. So now we can run the prover, right? This is the command, that script that runs the prover. It does not do anything special besides setting the resource limit. So if this model checker requires too much memory, it won't blow the computer. And basically, it just checks one C file by one. Okay, so let's run it. Again, it will take quite a lot of time. All these functions will be checked in about 6 minutes or so. So we won't wait until it finishes. Instead, we can have a look at the output of the tool. Let's take some sample function. Okay, this is an output of IDA, so you should be familiar with it. And we can have a look how it was translated into C code by UQBNT. This VSCLN instruction matches this one. And you can see that some assertions were added. And of course, assertions are not added after each arithmetic instruction. The reason why they were added is because somewhere below, okay, here we have a local alloc call. And if you backtrace the size arguments, somewhere it's assigned here, you will probably arrive at this point. Okay, so let's see how it works. In the assembly, you call VSCLN and multiply the results by 2, right? You shift EAX by 1 left. And we see it's translated properly. Okay, you can figure out that I24 is the representation of EAX register. So it's assigned the return of this function. And then you multiply it by 2. And again, you have to check for possible integer overflow. So you just check whether I24 is smaller than the half of the maximal integer value. Somewhere below, for instance, we have an addition, right? Add EAX15 in hex. And it should be somewhere here, I assume. Where is it? 15 hex is 21, right? Do you see any 21s in here? Okay, here it is. So we have this addition, and again, we have to check that EAX is smaller than maximum integer value minus 21. If it's smaller, then this addition is safe, right? No integer overflow can happen. Okay. Now let's go back to our tool. Okay, it has already processed a few functions. And you can see that in one case, almost in all of them, you have verification successful, right? But in one case, verification failed. And if you inspect this function more carefully, you will see that there is a real integer overflow in there, exploitable one, which is a nice thing. Okay, let's return to the statistic page. Okay, this many functions were generated. The important thing is that very little additional information has to be provided. I did not have to specify the calling convention of each of the function in the code, but only 3 of them. Only 3 did not comply to some heuristics. Also, I did not have to specify the meaning or the semantics of all library functions. I don't remember how many library functions were important, but in the order of 30, something like that. And I had to specify a simplified semantics of only 2 of them, vsclen and strlen. And it was important because it was necessary to suppress some false positives. Because you can assume usually that the value returned from strlen and vsclen cannot be arbitrarily large, right? Because you have to transfer the string over the network or anyhow, and cannot occupy more than 4 gigabytes, right? So the value is pretty limited. And as far as I remember, for instance, RPC specifications, the DCE RPC specification limits some size of the strings, right? So I had to specify that the size of the string is less than 16 megabytes, which well, it resulted in suppressing quite a few of false positives. And the full run of the checker takes about 6 minutes, and totally, it's 7 failed assertions alert are raised, right? So in 7 points, there are something suspicious. And if you analyze it manually, you get 3 of them are real bugs. So it's pretty nice. I haven't mentioned that, but of course, I ran these tests on the version of the binary from, September. So this is a vulnerable one, the one which was fixed by a recent Microsoft bulletin. So of course, this is not a new bug, but it was just a nice test to run it against a binary with known vulnerabilities. Okay, and finally, a few words about status and to-do. The code is highly preliminary. Well, it's put together by strings. A lot of work should be done to make it more useful and reliable. It should be made more configurable. Well, it should work better on pointers converted from integers. Because if you decompile the assembly, you often get such statements that some pointer is assigned an integer. And CBMC does not work too well on such input, so some additional work has to be invested in that. Better, type recovery. So if there are some classes or struct constructs in the C code, it would be nice to recover them because it will make the analysis more reliable. I think there will be some talk later today about automatic recovery of structures in the assembly, so that it could be quite instructive to listen to that. Another thing which is important is better support for computer execution and direction, like C++ virtual functions or optimized switch statements. Because again, in such case, it may be hard for a model checker to grasp correctly the execution flow. And some simple things could be added, like detect integer underflows in memcpy length, because currently I only check for overflows in memory allocation. And another thing is that integer underflow can happen in memcpy, calculation of the length, right? And this is some complementary issue, but it could be added pretty straightforward way. And of course, the ultimate goal is apply it to many binaries, find really 0 days, have fun. That's the main goal. Okay, I think we have time for a few questions.